Good morning, good afternoon, good evening, everyone. I hope you, your family, and your friends are all safe during these times. Welcome to Red Hat Virtual Summit. In this presentation, we will talk about a security overview of all the security features in OpenShift. My name is Anand Chandramohan. I'm a product manager with OpenShift Container Platform. And with me, I have Eran Tamir, also a product manager with OpenShift Data Foundation Platform. So OpenShift is a fully integrated and a fully automated container platform that allows for seamless Kubernetes deployment. The installation of Kubernetes is fully automated. You get one-click platform updates, and you can easily auto-scale cloud resources. As you can see from this deck, OpenShift installs on pretty much any type of infrastructure, including physical infrastructure like bare metal, virtual infrastructure like vSphere, private cloud infrastructures that you may have in your enterprise, public cloud infrastructure like AWS, GCP, Azure, and so on and so forth. And on top of this sits our operating system, which is RHEL and RHEL Core OS, which is the foundation for the OpenShift container platform. And we do ship a conformant and compliant version of Kubernetes. OpenShift is Kubernetes. And on top of this, you can install all your containerized workloads, your cluster services, application services, and developer services. And so OpenShift Container Platform is a hybrid cloud Kubernetes platform for helping you build and scale containerized application. And as you can see, there are multiple layers in the stack. So you need comprehensive security to help you build security into each layers of the stack, starting from infrastructure into operating systems, into the Kubernetes layer, and finally onto your applications. So the three facets of securing containers in OpenShift revolves around control, defend, and extend. So first of all, let's talk about the control pieces. So with the control pieces, you want to make sure that you have trusted container content, right? If you're, let's say, building a workload into a container, you need to make sure that that application, the workload that's running inside the container is trusted. You want to ensure that you're using a trusted enterprise container registry. You want to ensure that you are able to control and automate the process of building containers. And you're able to inject security into every aspect of the application pipeline, or what we call the secure supply chain for software. So that's the first piece. That's a control piece. Next is the defend piece. The defend piece is around making sure that you have the right platform configuration and lifecycle management for your software. You have identity and access management. So if you wanted to integrate with third-party identity providers, you have a way to do that through the platform. You want to make sure that you have a secure data platform, and you have secure storage that you can attach to the platform. And you also have secure deployment policies. You have audit logging, you have API management, and you have network isolation. And last but not the least, you want to be able to extend the platform into the broader ecosystem, right? So you want to integrate with third-party cert-managers. You want to integrate with third-party observability tools. You want to be able to secure application access. You want to be able to isolate your containers. So this is a comprehensive approach to securing containers in OpenShift. And in the next 30 minutes or so, we will go into each aspects of this secure container platform. So first, let's start with the defend piece. What does it take to secure the platform? As you know, a default install of OpenShift includes 3 masters and 3 nodes. The default install is based on the operating system that we call RHEL Core OS. And this includes, so securing this piece includes host and runtime security, identity and access management, role-based access control, project namespaces, making sure you have logging, monitoring, and auditing. You have network isolation. So basically ensuring that your operating system is secure and anything that you build on top of the operating system is secure as well. So let's begin with host security. It's like if I were to give you an analogy, if OpenShift were a car, the operating system that runs the car, which is basically RHEL and RHEL Core OS, are basically the tires of the car, right? And your enterprise operations team that is running OpenShift, needs to run secure containers at the boundaries. And that starts with making sure that the Linux kernel that OpenShift is running on, which is basically based on RHEL and RHEL Core OS, is secure. And that host kernel prevents container escapes. It makes sure that containers are secure from each other. They're adequately isolated from each other. And all this is provided through aspects of RHEL and RHEL Core OS, as we're going to see in this presentation. And containers at the at the end of the day are basically Linux processes, right, with isolation and resource confinement that let you run sandboxed application on a shared host kernel. And your approach to securing containers should be the same approach that you adopt for securing any process that's running on Linux. And any Linux container running on Red Hat OpenShift is protected by all the features of rel CoreOS that's built into the OpenShift nodes. So all aspects of rel security, like Linux namespaces, to make sure that containers are adequately isolated. Secure enterprise Linux, or what we call SC Linux, that pretty much builds a brick wall around every namespace. C groups, which is control groups that let you specify the amount of resource allocation each namespace should get. Other Linux capabilities, secure computing mode, which is seccomp profiles that basically restrict or confine containers from making protected system calls. So these are the whole bunch of features that rel and rel CoreOS provides, that basically extends to all applications running on top of rel and rel CoreOS. So next slide, let's talk a little bit more about rel CoreOS, right? So NIST special publication 800-190 recommends using a container optimized OS for additional security, right? You just don't want to use any operating system to be the backbone of your container platform. You want a purpose-built container operating system to power a container platform like OpenShift. And when you have a specialized container, purpose-built container operating system like rel CoreOS, you pretty much reduce the attack surface for the host environment, and you're tuning it for containers. And rel CoreOS is, think about it as a miniature version of rel. It contains only the necessary package to run OpenShift, and its user space is completely read-only. And this is, rel CoreOS is, tested, versioned, hardened, with OpenShift, and its installation is goes along with OpenShift. It updates are automated, and it's always compatible with OpenShift, right? And it pretty much supports the infrastructure of your choice, inheriting all the goodness of the rel container ecosystem. On top of rel CoreOS, we also provide something called the Red Hat Universal Base Image, which is Red Hat's container-ready operating system image that allows you to build smaller images for use in container-based systems, right? And this is basically something that's available in Docker Hub. And the bottom line is, if you're a developer, just pull the rel UBI image from Docker Hub and keep coding. Again, it's a very special miniaturized version of rel that makes life easy for developers. So next, on OpenShift 4 and FIPS 1.20, right? So FIPS stands for Federal Information Processing Standard, and it is a US government security standard used to approve cryptographic modules. When rel CoreOS is booted in FIPS mode, Red Hat OpenShift components call the Red Hat Linux cryptographic modules, and FIPS cryptography is mandatory for a lot of federal departments that ensure that sensitive data can be encrypted, and it is also necessary to meet some FISMA requirements and some FedRAMP regulations. So long story short, if you're in defense, if you're deploying workloads for the US government, most likely you will be asked to boot up an OpenShift cluster in FIPS mode. And the good news is we support FIPS mode. So next, container runtime. The container runtime that we support in OpenShift is called CRYO, that stands for Container Runtime Interface. And this is a lightweight alternative to Docker. As you know, as of Kubernetes 1.20, support of the Docker engine was deprecated, although users will still be able to use Docker images and registries. But the default runtime going forward from Kube 1.20 is CRYO, that provides enhanced security, that is Kubernetes native, and almost all the trusted registries like QA and whatnot, Docker Hub, accept CRYO-based images. So next is security context constraints, right? So security context constraints are a set of rules and regulations by which a pod running in OpenShift must adhere to and must behave, right? So there are about 9 security context constraints in OpenShift, starting with restricted all the way up to privileged. Restricted, obviously, being the most secure way of running the pod, and privileged, meaning it's the most you have access to everything, like accessing the host network or accessing host ID and whatnot, right? So there are, and all the levels in between are somewhere between restricted and privileged. And security, context constraints are, like I said, a set of rules and regulations by which pods must behave. They control the level of access a pod has on the host on which it is running, and if we want to guarantee that uh, uh, the pods has to behave with those secure best practices, security context constraints are what you need to use. And users can obviously adjust the level of SECs, and if they need some pods to be more permissive, they can adjust the SECs. If they need it to be less permissive, they can again adjust the SECs. Like I said, there are 9 levels of SEC varying from privileged to restricted. Protecting system resources, right? So again, chances are you're not going to bring up a cluster to run one workload or one pod for one team, for one user, right? Kubernetes, OpenShift is a multi-tenant platform, which means you can have multiple organizations, multiple teams, multiple users share the same cluster. And so you want to be able to define which containers are on which hosts, which host has access to how much capacity. How can containers talk to each other and discover each other, right? How do you manage access control? How do you scale applications? How do developers self-service? So all this is governed through the use of teams, limit ranges, resource quotas, with which you can create boundaries for teams. And then for those teams or for those namespaces, you can say these are the resources in terms of CPU, memory that those teams can use, so that you don't have a noisy neighbor problem. An administrator can decide ahead of time what the rules of the games are for each teams, right? So that's essentially how we protect system resources. And you can define projects, you can define quotas for each projects, you can define multi project quotas, all that's possible in OpenShift. Next is around protecting platform data, right? So etcd is a key value store that underpins OpenShift. So all the critical configuration data for OpenShift, secrets, volume mounts, config maps are all stored in etcd. Its health is extremely crucial. We provide an OpenShift a way to easily back up and restore etcd. So in case you have an outage, you can restore from a backup. And you can write a cron job to periodically take backups. Maybe write the cron job to an Amazon S3 storage or something, and then restore from it when you are trying to recover from a disaster recovery process. Right. You can also encrypt the etcd store. The etcd keys will be lying somewhere on the disk. So if you really wanted to encrypt the data, we have support with external key management systems like Vault that will help you encrypt secure data. Next, certificates, right? So certificates are used to provide secure connections between master and nodes, between etcd and API server. Your services need certificates. So all of this is completely managed by the OpenShift container platform. We ensure that new certificates can be minted as and when needed. We can integrate with third-party certificate management systems like cert-manager. We automate certs just before they expire. You can use custom certs for ingress endpoints for the console. You can specify custom routes, so on and so forth. Next, authentication. So OpenShift includes a OAuth server to manage authentication. But you do have a choice of integrating with up to 9 third-party identity providers. That includes GitLab, GitHub, Google, LDAP, HD Password, OpenID Connect, and so on and so forth, right? And the default user in Kubernetes is kubeadmin. That's the super user. And our recommendation is you install the cluster, you get kubeadmin, you integrate with third party, you set up your rules and roles and all your RBAC, and then you basically disable kubeadmin, right? So role-based access control, like I mentioned, is enabled by default. You also have the concept of service accounts. So in case pods need to call an endpoint to get access to a specific resource, they can use service accounts. You can use custom roles. And next, you can create teams within OpenShift, and you can create projects for those teams. A project is nothing but something that allows a community of users to organize and manage their content and isolations from other communities. End of the day, projects are just Kubernetes namespaces with SC Linux annotations. So as you can see in this slide, a particular user has access to a couple of projects, has access to a project called payment dev, but he or she does not have access to other projects like prod, inventory, and catalog, right? And the key thing to note here is projects. There are some internal projects. So projects that start with OpenShift hyphen or cube hyphen are default projects. Usually you cannot create resources under these projects. These are meant for the cluster. These projects host cluster components that run as pods, and you generally cannot create resource under these projects. You cannot extend these projects. But if you want to create new projects, you can just use the OCADM new project command, and you can create as many teams and as many projects and resources under those projects as you wish. And this is a good way of isolating applications across teams, groups, and departments. So if, let's say, you're an insurance company, you had auto line of business, property and casualty line of business, each teams needing their own resources, their own applications, but at the same time isolated from other teams, but still sharing the same multi-tenant OpenShift cluster. All this is facilitated with the use of projects and teams. So audit and log management, we do have integration with Elk Stack, EFK Stack, Elasticsearch, which lets you store logs, Fluentd that lets you gather logs and send it to Elasticsearch, and inbuilt Kibana dashboard that is basically serving as a UI for Elasticsearch. You can restrict control to these UIs and decide who can access these logs, who can see these dashboards. And whatnot. So a complete stack which lets you collect these logs using a cluster logging operator, which lets you collect logs from infrastructure, from pods, from workloads, from any other system resources, aggregate them, send them to Elasticsearch, and then visualize them in Kibana. And you also have a way of auditing your nodes, and you can choose which audit log policy profile you want to choose. There are multiple log audit policy profiles that you can choose, and based on that you get your desired level of logs that you can send it to any SIM of your choice. SIM stands for Security Information and Event Management System, and so this could be like Splunk, or it could be any other third-party system that you want. And so you could send all your event sources there, and you can visualize it there, or you can visualize a SIM data within OpenShift console itself using the EFK stack. So let's talk a little bit about defending the network, right? So far we spoke about how you can defend the operating system, how you can define Kubernetes, how you can defend all the workloads running on Kubernetes using things like security context constraints, SC Linux, and whatnot, projects, teams, namespaces. Now let's go a little bit up the stack and talk about how you can defend the networking pieces, right? Because ultimately, like I said, you're not going to have one user with one team with one application running as a monolith on OpenShift. You're going to have multiple teams, multiple users, each deploying their own set of microservices, running in a very distributed fashion. And all these microservices, are running as pods that need to communicate with each other. And, they need a networking layer that is secure so that they can, communicate with confidence, right? And so the networking layer in OpenShift is secure. We support multiple networking, plugins like OpenShift SDN, OVN Kubernetes, Calico, NCP, Cisco ACI, Cilium, Courier, Antria, a whole bunch of others. And all aspects of the network is secure, right? The east-west, the north-south. So when I say north-south, I mean the ingress into your cluster, right? We include a core DNS that is used to provide name resolution to pods. We include a HA proxy that supports ingress and routes. And as you know, HA proxy supports both re-encrypt and pass-through policies. So that's the way you would secure your north-south communication. And then your east-west communication can also be secure with network namespaces, using network policies, or even using a service mesh like Istio that we're going to talk about soon, right? And obviously egress, right? So if you had to communicate out from your cluster to, let's say, a database that is whitelisted, again you can specify how to control egress traffic. So long story short, east, west, north, south, all aspects, 360-degree traffic, in OpenShift is secure. Next, as I said, if you want to make sure that your east-west communication between pods are secure, and why do you need that? You need that because, like I said, an application could be composed of 10 microservices, each running in their own pods on their own nodes. And you need to make sure that, they communicate in a secure fashion. And so service mesh is, basically, based on the open source Istio project. It adds a transparent layer on top of, OpenShift. And you can secure the traffic between pods without making any change to the pods or the application code itself, right? So if you want to, let's say, restrict pod A from talking to pod B and say pod A can only talk to pod C, right? You can specify that in Istio or in the service mesh without actually making any code change to the code that's running in pod A, B, or C, right? And so, service mesh provides this, discovery, load balancing, service to service, communication, authentication, encryption, and whatnot. And as you can see from this, this small tile below, you can specify, who can talk to who and how. And you can visualize all these interactions in the tool called Kiali. So next, I'm going to hand it out to Iran to talk about how we can defend the data that's, underpinning OpenShift. So over to you, Iran.
Thank you. So in that section, we'll talk about data protection and specifically how we can provide it by using OpenShift Data Foundation, also known for part of you as OpenShift Container Storage. So let's get started. So let's start with the underlying storage. We would like to encrypt all the underlying storage devices that we consume by OCS. That helps us to protect from disk theft and also allow easy RMA if you have a failure in your storage, in your local devices, so everything will be safe. By default, we do it automatically with provisioners that has the support that. If they don't have the support, it's very easy to encrypt the host devices externally, and from OpenShift Container Storage, it will be transparent. Next in line is the way that we protect object storage. So for those of you who don't know OpenShift Data Foundation, we have block, file, and object. So let's start with the object storage. The object storage is encrypted by default on the service side, but as you know, it's always about layers, and we don't assume that this is enough. So we also support customers to use bring your own key, and also use managed keys that I will elaborate later on. We want to make sure that we protect the object from any compromises from the gateway, not just by credentials, but also if someone gets hands on the underlying infrastructure, we want to make sure that the data is not compromised. How we do it, again, we can provide customer to use their own keys that are managed externally and not within the OpenShift platform, and that helps to separate from key and data and avoid someone unauthorized to decrypt the data. Next support is the entire cluster encryption. So if you're using OpenShift Data Foundation, you can easily decide that you can encrypt the data on the OpenShift Data Foundation level. Why should I care about it? Sometimes I don't have the access or I don't have the capability to encrypt the local storage, the underlying storage. And in that case, I would like to have the encryption on the OpenShift Data Foundation level. Sometimes I would like to have both because I get different level of protection from each one of these security layers. So with the OpenShift Data Foundation, I can protect the entire cluster and make sure that everything is encrypted, regardless if I'm using file, block, and object. And it's very easy to do it. How easy? You can see in front of you, that's the screenshot from from the OpenShift console, and OpenShift Data Foundation is integrated into the OpenShift console. And during the deployment, you can simply enable the encryption, and that's it. You get a cluster-wide encryption, no other configuration, nothing else to worry about. Everything is encrypted from that point and on.
So the next step would be using encryption for the entire cluster with external Vault key management system. What we have here is an entire cluster encryption that we integrated with external Vault key management system. It includes the entire cluster encryption, includes the PV level encryption that I will talk about in a minute, and also the object storage. Why do we need it? Because whenever we have data in one place and the key managed also in the same place, there is a risk for the data that someone can get access to this location and can get the ability to actually decrypt the data by separating physically the keys from the data, and we get a better protection. And like always with OpenShift Data Foundation, we want to make sure that everything is easy. And how easy? Let me show it to you. So as you can see here, during the deployment, and another click here would on the connection setting would help me to actually connect to an external key management service. I can select the provider. In this case, it's Vault. I will name it. I will provide the address, the port, the authentication token, and basically that's it. From that on, from that point on, all the cluster is encrypted. The file, block, the object, everything is encrypted, and all the keys are stored in the Vault key management system, and we don't need to worry about it. If we want, we can also rotate the keys from the Vault side and make sure that everything is maintained properly. The last layer that I would like to introduce is the persistent volume encryption. The persistent volume encryption is another granularity that we provide with OpenShift Data Foundation. We let customers to actually encrypt every persistent volume with a distinct key, and also we provide a way to separate tenants by namespace, which means that every storage cluster that we create have the optional configuration to use a different authentication token with a Vault key management system. And by that, we allow customers to protect the observability even by storage administrators. So every tenant can access only their own PVs. Every token can be used only for specific tenants. These tokens managed in Vault key management system and namespace feature. And how do we do it? Again, very simple. If you'll take a look at the screen here, you will see that when you create a storage class, you can simply enable encryption on the storage class level, provide the same information, the provider, the service name, the address, the port, and also the token. And with that, you are done. And again, there is also an opportunity to use different, even different key management systems, instances, or even provider in that case. But currently, we support only the HashiCorp Vault system. That's it on my side. Thank you.
Thanks, Ron. So far we've talked about how you can defend all aspects of applications running on OpenShift, right? Defending the container platform, defending the operating system, defending the data, defending the workloads. Now let's talk about how you can control the apps that's running on OpenShift. So you can integrate security into every aspect of your DevSecOps lifecycle or your CI/CD pipeline. And you can simplify, the whole DevSecOps story by providing developers automated guardrails within their existing workflows. Red Hat Advanced Cluster Security integrates with your CI/CD pipelines, image registries, and provides continuous image scanning and assurance. And we shift security to left, and that way vulnerable, misconfigured images can be remediated within the same developer environment with real-time feedback. And as you know, the last couple of months, we acquired a company called StackRox, which is a Kubernetes native security provider that offers features like vulnerability management, compliance, network segmentation, risk profiling, config management, and so on and so forth, right? And so this is just an example of how you can integrate security into every aspect of your CI/CD pipeline, or what we call the secure, supply chain. Make sure that we have quality assurance for your images. Your images are trusted, are secure, they have the right content in it, they're certified. You can sign images, secure images, and you can distribute them through only secure channels. And so, when you're, building applications and distributing them, through CI/CD pipelines and, other, DevSecOps pipelines, you have a couple of questions that come to mind, right? Is the container content going to, compromise your infrastructure, right? For instance, do you have malware running inside container, or it's some, malicious, ransomware get into your container image that's going to, run in your data center? You want to know if there are vulnerabilities in the application layer. You want to know if the runtime and the OS layers are up to date. For instance, is the rel image up to date? Is the Java runtime running on top of it up to date? So on and so forth. You want to know how frequently the container will be updated and be notified when the image will be updated, right? So we provide a registry called Red Hat Quay, which is basically available as a standalone enterprise registry. And Red Hat Quay offers many enterprise features like geo-replication and build image triggers. And Red Hat Quay is backed by a open source project called Claire. Claire is basically an open source engine that powers Red Hat Quay security scanner to detect vulnerabilities in all images within Red Hat Quay, right? And the Red Hat OpenShift container security operator that you can get from the Operator Hub or from the Red Hat catalog integrates with Red Hat Quay to provide a cluster-wide view of known vulnerabilities for your deployed images within the OpenShift console. And going hand in hand with Red Hat Quay and Claire is this other feature we have called the Container Health Index, which is basically a web page where you can go look at the grade of each container image, detailing how the container image has been curated, consumed, and evaluated to meet production needs. So let's say you're consuming an image for JBoss, or you're consuming an image for let's say some other middleware component that runs on OpenShift. You want to make sure that the image is patched, it's secure, it's up to date, and you can look at the grade. We do grading like A, B, C, D, F. A means a very high score, and then the lower it goes, the lower the score. And so you can be rest assured that if a container image has a high grade, this has been properly vetted by Red Hat. And the container index, health index, is again a web page that you can go to that exposes the grade of each container image that you use in your deployment. Next, secrets management. Secrets stored in etcd can be encrypted at rest. But like I said, if you really had any secret data to store, I would highly recommend that instead of storing the data in etcd, because end of the day, etcd, although it can be encrypted, the keys are lying somewhere on the disk, and if somebody has access to those keys, they pretty much get into etcd and they pretty much get access to all your secrets. So a rough analogy is like just kind of locking your house and leaving the keys outside. So I highly recommend that you make use of an external key vault, key management system like Vault, to store any secure data that you may have. Next is container signing. We recommend that you sign all custom built containers so that they're not tampered with between build and deployment. And this is just a workflow of how you can sign images. As you can see, a developer starts a build and he pushes the build to a registry. He also creates a image signing request that basically kicks off a signing operator that creates a signing pod that pulls the unsigned image, signs it, and then pushes it back into the registry. So the last part of our presentation is going to be around extend. So we have seen how you can defend and how you can control applications running on OpenShift to offer more secure features. Now we're going to talk about how you can extend the broader ISV ecosystem. And as you can see from this slide, Red Hat is obviously built on open source. It's built on open standard, and this makes it extremely easy for our partners to integrate with OpenShift and for you to extend the platform with custom connections to tools that you may already be using. For instance, you may be using Dynatrace for monitoring. You may be using Instana for monitoring your APM applications. You may be using MongoDB as your database. You may be using Tufin for network visualization, or you may be scanning images using Twistlock, and so on and so forth, right? Since we built on open standards, we make it really easy for you to consume any third-party application. And particularly if you're interested in network security, you may want to consider some of our network partners. Like, when it comes to application cluster health, you may want to look at CoScale, Dynatrace, and Sysdig. For identity and access management, you want to look at CyberArk. For certificate management, you want to look at cert-manager, which comes from a company called Venafi, that is made cert-manager open source, and so on and so forth in this list. And end of the day, we want to give you peace of mind when we work with customers and partners to develop new features and functionalities. We want to make sure that you have complete peace of mind. You're betting on a trusted platform, you're betting on a secure platform, and you're betting on a platform that has been hardened with security. And this is just to show you that we take somewhere between 1 to 3 months to harden an upstream Kubernetes release with security fixes. We patch like hundreds of defects. We look at performance fixes. We run through 200 plus validated integrations. We validate our middleware components like AMQ and whatnot. And we are a certified Kubernetes vendor, right? And this is not to say that we are slow behind upstream Kubernetes. In fact, if you look at some of our competition like GKE, they are about 2 months behind. PKS is about 3 months behind. So the point being, we are taking this time to harden out the platform so that we are ready to be an enterprise Kubernetes that is secure, stable, and fully integrated with the whole ecosystem. And telemetry is one of the things that we optionally capture from your OpenShift cluster, so that we product managers, we Red Hat OpenShift as a company can use to understand more about the way you're using our product, and if there is any proactive actions we can take for you to offer enhanced support, we can offer that. So this is something that we can collect as an optional basis if you want to share that with us, so we can make some proactive recommendations based on the way you're using OpenShift. And obviously, if you buy the Red Hat subscription, you have absolute peace of mind. That all the workloads are supported. It's a fully hardened platform, right from the operating system to the Kubernetes, to the applications, to the network traffic, to the storage, to any third-party components that are running on it, to the entire secure software supply chains that's feeding into OpenShift. All of that secure. You have 24/7 access to Red Hat support engineers, access to all training, product documentation, solution documentation, and whatnot. And so I will just end the presentation with this diagram. Again, rounding off, we saw how you can defend OpenShift, how you can control all secure aspect of OpenShift, how you can extend all security aspects of OpenShift, right? And this is basically our defense in depth story, right from our container host running RHEL Core OS, to the Kubernetes control plane, to the secure software supply chain that's running on top of it. Every aspect of the stack is secure. So Linux is secure because we run on RHEL Core OS that supports things like FIPS mode. The control plane offers an OAuth server, also supports integration with external IDPs. Our data is protected at rest and in motion. Our images that you deploy to OpenShift are secure. We use things like Claire for scanning images. Obviously, we have integrated auditing, logging, and monitoring with the EFK stack. We have security policies with security context constraints and whatnot. And you have network isolation with the OpenShift SDN that can control ingress traffic, with network micro-segmentation with tools like service mesh that's based on Istio and whatnot. So essentially the network, the data, the workloads, the images, the operating system, the platform, the whole ecosystem is absolutely secure and locked down. With that, I will end this presentation and we can move on to any questions that you may have. Thank you.